Welcome to the NPTEL lecture series on quantum computing. I am Ramakrishna from IBM Research, and I will be delivering lectures this week along with Professor Prahamandyam of IIT Madras. This week's lessons are divided into 4 modules where you will learn the basics of quantum computing, and we will discuss ideas from quantum mechanics and mathematics that are foundational to understanding the subject. The lessons you learn this week will also lay the basis for lessons you will learn in subsequent weeks, where you will learn how to develop quantum algorithms and program on real quantum computers. In the first module, you will learn what the basic units of quantum computing are, namely quantum bits or qubits. But first, we will briefly discuss why quantum computing promises to be a game changer in the field of computing and why this is such an exciting subject to study. Next, for those of you who are already familiar with classical computing as programmers, we will briefly compare quantum computing to classical computing concepts. Next, we will provide you a brief background in linear algebra, which is the mathematical foundation that all of quantum computing is based on, and present some brief mathematical notation. The rest of the lecture will be devoted to understanding qubits and their representation both in mathematical and in visual terms. Today's computers can solve a wide variety of problems, but there are certain classes of problems that are too hard even for the most powerful computers that we have today. And this is why we need quantum computing. Now, to understand this a little better, we need to understand how to compare two different problems or two different programs in terms of their hardness. So take a look at this graph. The curves on this graph represent the complexity of a computer algorithm or a computer program. The y-axis represents the time or the space that any program can take, and space can be measured in terms of computer memory. The x-axis represents the size of input that we are feeding into a program. So the steeper the curve, the harder that particular problem is, or the harder that particular, or the longer and more resources that particular computer program will take. So you can see there is certain simple polynomial functions plotted here. There's a linear function which is not very steep at all. Then there's a quadratic function which is very steep. And then there is a function n log n which has a degree somewhere in between 1 and 2. Now let's add a few more functions to this midst. We'll add another polynomial function, n to the power 5, and then we'll add two exponential functions, 2 to the power n and 5 to the power n. You can see these two functions are at the left of your screen, and they're basically off the charts. They just shoot up immediately for even for very low input sizes. What does this mean? Let us expand the y-axis range to take a closer look. You can see now our quadratic function is slightly less steep, whereas our linear and our n log n functions are almost flat, which means for higher input sizes, the time and the memory that is consumed for more complex functions just doesn't compare to simpler functions of linear or quadratic form. Now, increasing the y-axis range even further, we see that our polynomial functions up to n square just cannot be seen at all. They are almost super fast when we look at it at scale. Now, our polynomial function has just started to separate from our exponential function, but our exponential functions still rise almost vertically. And here, when we increase the y-axis range even further, there comes a time when any polynomial function will almost look flat. But even the simplest exponential function, like 2 to the power n, still rises up basically steeply. So you can imagine what's happening here. Computer programs that can perform or that take a polynomial amount of time or memory compared to the input sizes, for higher input sizes can perform rather well. But exponential size programs, that is, programs that take an exponential amount of time or an exponential amount of space, just cannot be solved tractably with today's computers. And that's the intuition we're trying to provide with these set of graphs. Now, moving from a linear scale to a log scale graph, you can see the same thing. The polynomial functions essentially flatten out, whereas the exponential functions rise linearly, which is as expected because it's on log scale. Now let us zoom into the bottom left-hand corner of this graph and show you something interesting. You can see here the n to the power 5 curve does not always perform better than our exponential curves. At lower values or at lower input sizes, it can actually dominate our exponential curves. First, it can even dominate n to the power 5 or 5 to the power n, and later it can also dominate 2 to the power n for a little longer until it then goes below that curve. What does this mean? This means that at lower input sizes, a polynomial function can actually grow faster than an exponential function. Depends on what the polynomial degree is and depends on what the base of the exponential function is. But what this means is that our classical computers that exist today, which can solve functions or programs that grow polynomially, are still going to be relevant when we have quantum computers. Quantum computers promise to solve problems that are inherently exponential, that is, which have exponential size increase in time or the requirements of space as the input size increase. But for lower input sizes, classical computers may actually end up performing better than quantum computers. So that's a lesson we want to leave you with here. Okay, moving from our motivation, which I hope was sufficient for you to appreciate why we need quantum computing, let us see how quantum computing compares with the classical computing that many or most of you are already familiar with. In classical computing, as you know, the units of computation are bits or binary digits, 0 and 1. And these represent the states that any computer unit can take. In classical computing, the basic units of computation are binary digits or bits, 0 and 1. And these represent states that any memory unit in a computer can take. In quantum computing, the comparison is with qubits, or what are called quantum bits. And these quantum bits can be in states that are loosely equivalent to 0 and 1 that you see at the left. But these are thought of better as unit vectors rather than states, as you will see in the later slides. A qubit can be more than a 0 and 1 though. It can be a linear combination of a 0 state and a 1 state, as you see at the right. And the coefficients in this qubit, alpha 0 plus beta 1, that is alpha and beta, are complex numbers. And this is called a superposition state. That is, a qubit can be in a superposition of two basis states, 0 and 1. And again, we will delve into these concepts in detail in subsequent slides. But suffice to say that in classical computing, we only have two states, whereas in quantum computing, you can have qubits that lie on a continuous scale. And that's what we see here. A state or a bit can assume only one of two values, 0 or 1, whereas the qubit can assume any value alpha 0 plus beta 1, where alpha and beta are any complex numbers. What does this mean? It means that in classical computing, the state is deterministic, whereas in quantum computing, a qubit is not in a definite state, but rather it has the probability to be either in the 0 state or in the 1 state at any given time. And this probability can actually be measured accurately if we know the coefficients of 0 and 1, that is alpha and beta. As you can see, that's the probability of qubit being in state 0 is mod alpha square, and being in state 1 is mod beta square. Again, we will come to these concepts in detail, but suffice to say for now, classical computing states, once you know the state of a bit, it's set at that, whereas in quantum computing, a qubit can be an arbitrary value, but what you perceive of a qubit is a 0 or 1 at a given probability. Now let's look at the gates or the computational methods that are used in classical computing versus those used in quantum computing. If you're familiar with classical computing, you know that we have several kinds of logic gates, or what are actually Boolean gates. One example being a NOT gate. In quantum computing, the equivalent of such a NOT gate is what we would call a poly X gate. Again, a concept we will learn in one of the subsequent modules in this lecture. In classical computing, the computational mechanism or the computational framework used to reason about gates and how they convert an input to an output is Boolean algebra. So here, in Boolean algebraic terms, NOT is simply a function that converts 0 to 1 and 1 to 0. In quantum computing, on the other hand, we need to use a more sophisticated mathematical framework, that is linear algebra, and the gates are actually represented by matrices and not simply a Boolean function. So in linear algebraic terms, the poly-X gate is actually applying a linear transformation, or basically multiplying our state with a matrix to produce a different state being qubits. So in this case, the X gate applied to a 0 state or a 0 qubit will produce a 1 qubit, and when it's applied to 1 qubit, it will produce 0 qubit. You can see the equivalent there between classical computing and quantum computing, but the difference is in the internals. The mathematical framework used here is much more sophisticated and complex. Lastly, if you want to use the poly-X gate you apply it to an arbitrary qubit, alpha 0 plus beta 1, you end up flipping the coefficients. Alpha moves to 1 and beta moves to 0. Again, we will see how the mathematics of all of this works later in this lecture. Take another example from classical computing, the AND gate. And here is a rough equivalent in quantum computing, where you can have a set of qubits or a multi-qubit state that to which a quantum gate can be applied, and which gives you a multi-qubit state as output. Now, in classical computing, you will see that when we take B1, B2 as inputs and we produce B out as an output from the AND gate, this operation is irreversible. Once you get B out, you cannot actually recover B1 and B2 from B out. But in quantum computing, this operation or any such operation is reversible. If we provide a multi-qubit state Q1 up to Qn and we feed it to a quantum gate, and we get as output state Q1 dash up to Qn dash, you can actually recover Q1 through Qn from Q1 dash through Qn dash. And this is something that is just not possible in classical computing, and whereas it's foundational to quantum computing. So this is one of the big differences. Finally, in classical computing, because our states are definite, that is, our bits always lie in definite states, the state space that we can deal with using one or more gates, which is really the foundation of any computer program, is linear in the size of the input. Whereas in quantum computing, because our states are superposition states, we can end up creating from n qubits a state space of size exponential in the size of the qubit set. That's 2 to the power n, and that this gives us a lot more computing power. So we can apply with n qubits, we can actually perform operations on a state space of exponential size. And again, this you will see in the subsequent lectures in this module, as well as you will see how to do this in practice in quantum algorithms and quantum programming in the next few weeks. Okay, now let's jump into the quantum computing basics, having covered all of the comparisons and the motivations. First, we will discuss the mathematical notation that is foundational to understanding how to think about quantum units and how to reason about them and their transformations. So the basic notation you will use here, and which you will see is a very convenient way of dealing with quantum states, is the Dirac notation, or what is also called the bracket notation. The ket is the most basic object that you can get in quantum computing, and a ket is represents a quantum state, and as you will see later, it represents a qubit as well. Roughly, you can think of a ket as being the equivalent of orthogonal unit vectors in a 2D vector space. If you can think of a two-dimensional vector space with the I and j vectors on the x and the y axes, the ket 0 and 1 are roughly equivalent to that, and they are also equivalent in linear algebraic terms to column matrices. So in linear algebraic terms, the ket 0 can be represented as a column matrix of 2 rows, first row being 1, second row being 0, and the ket 1 having the first row 0 and the second row as 1. More generally, any ket psi can be represented by as the linear combination of the kets 0 and 1. That's why you see alpha 0 plus beta 1. Again, if you can imagine this in two-dimensional space, you think of it as an arbitrary vector that you plot on that space, which will be a linear combination of the I and j unit vectors. Except think of the coefficients as being complex numbers. The equivalent of this in matrix or linear algebraic terms is a column matrix with a single element in each row. And this element is actually an element in a what is called a complex Hilbert space, which is a vector space. And this element or this ket, which can be represented as a single column 2-row matrix, is a linear combination of two orthonormal basis states, which is what you see here. Now, what is a Hilbert space? So Hilbert space is really an extrapolation of a two-dimensional space to n dimensions. So if you think of a 2D plane with an x-axis and a y-axis, and you have a unit vector that aligns with the x-axis and a unit vector that aligns with the y-axis, you can represent any point on the 2D space as a linear combination of the unit vectors of the x and the y, right? The Hilbert space is nothing but an extrapolation of two-dimensional space to n dimensions, and the coefficients are complex numbers. So the mathematics remains very similar. It's just that you have a different kind of space. And the standard basis is roughly equivalent to your I and j vectors on a 2D space, and these represent what are called orthonormal basis states in linear algebra. That is, they are perpendicular to each other in a way of speaking. So the bra, which you can see looks like the reversal of a ket, is actually an operation or a function that you can apply on any ket. And it's reversed because, as you will see in the next slide, it can be applied to a ket to produce something useful. And for a given ket, we can compute a bra as the conjugate transpose of a ket. What is the conjugate transpose? Just refreshing your complex numbers and matrix theories that you may have learned in high school. Think of a complex number alpha being having a real part A and an imaginary part B. Its complex conjugate A star is A minus IB. That is, keep the real part the same and negate the imaginary part. And for a matrix, the conjugate transpose is defined as A dagger. So for a given matrix A, its conjugate transpose A dagger is defined as the complex conjugate of that matrix's transpose. So you take the transpose of the matrix A, and then on each element you apply, you change the element to its complex conjugate. That's the conjugate transpose, or A with the dagger symbol at the top right, as you can see. In matrix terms, if the ket is a column vector, the bra is a row vector, as you can see. So a ket has alpha and beta in the two different rows. Bra has a single row with alpha star, that is the complex conjugate of alpha, and beta star, complex conjugate of beta, in one row. Okay. So this page shows you kets and bras of two dimensions. Now these are simplest kinds of kets and bras that you can encounter. Let us generalize the ket and the bra beyond two dimensions. Okay. Take a general ket psi, which is actually an n by 1 matrix, and a bra phi, which is an n by 1 matrix. Okay. Now there is a particular operation we can perform called bra ket, which applies the bra operator to a ket vector. You can see here it's represented with this notation, which is the bra joined to a ket, and this is actually the inner product of the bra and the ket, or rather is the inner product of the vectors, vector represented by phi and the vector represented by psi. So think about vector dot products in a two-dimensional vector space. Okay, when you do dot product, you get a scalar, right? Similarly, here the bra ket produces a scalar quantity. In this case, it ends up being a single complex number. Take an example from above. The bra is a 1 by n matrix and the ket is an n by 1 matrix, right? So it is nothing but the multiplication of those two matrices, and The output here ends up being a 1 by 1 matrix, which is nothing but a single quantity, a scalar, or in this case, it's a complex number. Taking some concrete examples, let's apply the bra of 0 to the get 0. Okay. Now the bra of 0 is simply this row matrix, and we know this is the get 0. If you do the matrix multiplication, you simply get the quantity 1. The bracket of 1 and 0, on the other hand, it gives us the quantity 0. You can relate this to your vector spaces, where if you take the scalar product of two collinear vectors, you end up reinforcing them, right? Whereas if you take the dot product of two orthogonal vectors or perpendicular vectors, because their projections onto each other are 0, they end up being 0. Similarly, you can see the intuition behind bra and the get here. This is just called the inner product in linear algebraic or Dirac terms. Now the get bra is the reverse thing to a bracket, and you can see here in even the notation is reverse. You just have a get followed by a bra. What does this mean? Our bra is an operator, right? The get bra simply changes our one operator into another, and it's called an outer product in contrast to the bracket, which is an inner product. And let's just see what this produces. Our get is an n by 1 matrix, our bra is a 1 by n matrix. If you multiply them, what do you get? You get an n by n matrix, right? And that's what our outer product is. It's an n by n matrix, but then in linear algebraic terms, any matrix is a linear transformation operator, right? So you end up producing a different kind of operator, and you will see this kind of operator will come in very handy when we do quantum computational calculations. And having a shorthand of this form, the get bra, instead of this big matrix, can be very useful. So let's go into single qubits now, which are the basic units of computation in any quantum computing system. A single qubit is nothing but a vector in complex two-dimensional Hilbert space, and it can be represented very generally as an arbitrary get, which is the linear combination of our orthonormal basis states 0 and 1, whose inner product is 0, and the coefficients happen to be complex numbers. The matrix representation of this is 2 by 1 matrix, as you've already seen. Now, our qubits or our quantum states, though generally they can be described as a linear combination of basis states, or in other words, they can be described as a superposition of a 0 and a 1. When we actually look at those qubits, they probabilistically collapse to either of those two basis states. So they do not remain in the superposition form. When you look at them, they collapse. So they can assume the form either 0 or 1, and as it happens, their probabilities of assuming the form 0 or the form 1, or rather, in other terms, being in the state 0 or being in the state 1, happens to be definite, and we can actually calculate this. Before we attempt the calculation, just a refresher on complex numbers. If you take an arbitrary complex number, alpha equals a plus ib, or using polar coordinates, it can be expressed as r e to the power I theta. Its modulus is nothing but root over a square plus b square, or r if you take the polar coordinate form. So let's look at the probability of our qubit q being in state 0, and that is given by this particular formula. The formula is, look at the internal term, it's the bra 0 applied to the ket q that we have here, and then when we get the after we get the bra compute the bracket, we get a complex number, right? We take the modulus of that and we take the square. Okay, now let's do the math here. So let's expand q, which is alpha 0 plus beta 1. Now, because all the operations we are doing here are linear transformation operations, we can distribute as well as take scalar parts of an expression out, and that's what we'll do here. We'll apply the 0 to this term, and we'll apply the 0 bra again to this term. What do we get? We can take the alpha out, and we get the bra 0 applied to the get 0, plus we take the beta out, and we have the bra 0 applied to the get 1, and we take the modulus and the square. Now, as you have seen, the bracket 0 0 is 1, and the bracket 0 1, because they are orthonormal basis vectors, is 0. This term vanishes, and all we are left with is alpha. So we get mod alpha square. Similarly, the probability of Q being in the state 1 or the qubit Q collapsing to state 1 ends up being mod beta square, and the math here is identical to what we just saw. And as it turns out, mod alpha square plus mod beta square must add up to 1. Why is that? All the qubits we're going to be dealing with must have if you take the equivalent bra and you apply it to that qubit as a ket, they must end up being 1. And this is called a normalized state. So we are only going to be dealing with what are called normalized states or normalized qubits. And the idea of normalization comes from quantum physical requirements, but you can see why this requirement exists. You have the probability of our qubit collapsing to either the 0 or the 1. It can't collapse to anything else, right? Therefore, the probabilities must add to 1. And note that alpha and beta are also referred to as probability amplitudes for a general qubit. You'll learn more about the quantum physical requirements and the intuition behind this in the subsequent modules this week, which are delivered by Professor Prabhamandiam. Having covered the mathematical representation, let's try a visual representation of a qubit. Okay, and the tool we can use for this is called a block sphere. This sphere is simply it's any general sphere with an x-axis, a y-axis, and a z-axis. And note that our z-axis has at its extremities, or the north and south pole, our standard basis vectors 0 and 1 respectively. Okay, and we'll come to that in the next slide. Take any arbitrary qubit, Q, which is alpha 0 plus beta 1. Turns out we can use a block sphere to represent this qubit Q in a visually intuitive way. Any qubit Q can be represented as a point on the surface of the block sphere. Okay. So let's see what more use we can get out of block sphere representation. The moduli or the probability amplitudes alpha and beta can be represented using polar coordinates, right? So let's assume alpha is r1 e to the power I theta 1, beta is r2 e to the power I theta 2, and because Q is a normalized qubit, r1 square plus r2 square must add to 1, as we saw in a couple of slides before. Note that this expression is independent of both theta 1 and theta 2, and we'll come to theta 1, theta 2 later. But in this particular expression, note that we can use represent r1 and r2 in terms of trigonometric functions. So because the square of a cos of an angle plus the square of that angle's sine must add to 1, we can assume r is the cos of a particular angle, let's pick theta by 2, and r2 then must be the sine of that same angle, theta by 2, and this adds to 1 for any value theta. Why do we choose theta by 2 and not theta? As it turns out, it's because then we can represent any arbitrary qubit Q with an angle theta to the z-axis and oriented towards the north pole. Okay, let's understand this a little bit more. Let's assume theta to be 0. So what do we get? Cos 0 is 1, right? So r1 must be 1. Sine 0 is 0, so r2 must be 0. And if theta is 0, that means this is 1 and this is 0, or Q becomes simply state 0. And that is why you see the vector 0 or the ket 0 at the north pole or at this extreme end of the z-axis. Similarly, if we take theta to be pi, then cos pi by 2 is 0. R1 becomes 0. So this term cancels out, and sine pi by 2 is 1, right? Or sine 90 degrees, that's 1. So beta becomes 1, so we get Q becoming vector 1. And so if theta is pi or 180 degrees, our qubit Q is nothing but the vector 1. And hence we have our z-axis at its extremities with the 0 and the 1 kets. Hope that's understandable to you. Also note that our representation in the block sphere end up doubling the angle between qubits and the basis vectors, as you would see in the Hilbert space, right? So in a Hilbert space, and for intuition, just assume a two-dimensional space. Our basis vectors 0 and 1, or I and j unit vectors, would be perpendicular to each other, right? But here our basis vectors 0 and 1 are have an angle of pi with each other, which is double. So that's another intuition you can take. That's why though the mathematical representation has a theta by 2, in visually the term theta is what matters when you look at the angle between the qubit and the z-axis. Now let's consider our argument part or the complex part. So we have theta 1 here and we have theta 2 here, right? Associated with alpha and beta respectively. Without lots of generality, we can assume theta 2 equals theta 1 plus some angle phi. Okay. And note that only this relative phase phi matters, because whatever be theta 1 and theta 2, we can have this expression, and they will have some difference with each other, right? So if we set in this expression, let's just set theta 1 to be 0, then theta 2 simply becomes phi, or the difference between theta 2 and theta 1. And if we do that, then our original expression changes to cos theta by 2 phi 0 plus e to the power I phi sin theta by 2 1. Okay. Now we have no more complex part associated with 0, and we only have the complex part associated with 1. And if you look at the Bloch sphere here, this angle phi, if we take this expression, ends up being the angle between our qubit q, or the vector q, and the x-axis. So you can look at the projection of q onto the xy plane, and then the angle with the x-axis is going to be nothing but phi. Now, how can we just set theta 1 to be 0 and therefore just use phi rather than having two separate values for theta 1 and theta 2? Think about our sphere, right? This is a sphere. We can have the sphere in any frame of reference, or at in any rotated position. So as long as we put in a position where we assume that one of the thetas can be 0, then our vectors can be represented using simply the difference between the thetas. So we have the freedom to rotate our sphere in any way possible, and that really is the intuition behind this, or behind just using the relative phase rather than the absolute phases, because we are not forced to have our sphere in any particular orientation. The sphere is our entire space, and we can choose to put it in any position so that we can deal only with the difference between the phases of the two parts of Q. Now, this qubit relative phase, or the rotation, in other words, around the z-axis. Okay, the angle is with the x-axis, but really, think about it, the relative phase means how much a qubit has rotated around the z-axis. This also has no analog in classical computing, just like the concept of superposition. So that's another big difference you should note between quantum and classical computing. You'll learn more about the physical intuitions, as well as some more intuition about basis states as well as phases in the subsequent modules delivered by Dr. Rahamandyam. But for now, just keep in mind that we can represent any arbitrary qubit on a Bloch sphere using simply two angles, theta and phi. Let's take some notable examples of single qubits before we close out this module. So if you look at the Bloch sphere, our vector 0, or our get 0, is at one end of the z-axis, and we have already seen can be represented by a single column vector. Similarly, the qubit 1 is at the other extremity of the z-axis. Another special vector is at one end of the x-axis, and that we call as a plus vector, and that is the superposition of 0 and 1, and our alphas and betas here are both 1 by root 2. Okay, in matrix terms, this can be represented as this 1 by root 2 and 1 by root 2. And note that if you take the square of the probability of the moduli and add them, you'll get half plus half and 1. So therefore, you can see that the plus state is a normalized vector. Similarly, our minus state lies at the other end of the x-axis, and it's similar to plus, except that the sign on the 1 is a negative. At both the ends of the y-axis, we have what we call the plus I vectors and the minus I vectors. Okay, and this is also, plus I is very similar to plus, except that you have an I associated with 1. Now note that when you take the moduli of 0 and 1, you square them, add them, the imaginary part plays no role. So you can do a half added to a half, and you get a 1, right? So that tells you that these the plus I vector and the minus I vector are also normalized. So this concludes our first module, and let's just summarize what you learned and what you're going to learn in the next few modules. Thus far, you've learned about the key differences between quantum and classical computing, and you've learned about qubits, the linear algebraic concepts that underlie them, and their visual representations using the block sphere. Next, you will learn about the quantum physical basis of qubits. You will learn more mathematical details about quantum states, as well as the basis states that they are linear combinations of. And you will see how to measure quantum superposition states. Okay, we alluded to this when we talked about how a qubit collapses to a 0 or 1 state. You will find out what the notion of quantum state measurement is and how we can measure quantum states. See you next module.